compute at each point n. Then we had a function g of theta. If we multiply this n times, we get g of theta to the power n. And then the exponential becomes eta transpose sum of the u's. Right? Nothing fancy. But what is interesting is, when you do this calculation, immediately you see that this data likelihood also belongs to the exponential family, right? So it's not surprising. We have been surprising if that was not the case, right? So if you take the log of this, all right? So we're going to have the summation. Did I forget something here? No, this is good, all right? We forgot the log here? No? Okay, so it doesn't matter, this doesn't depend on eta, okay? So we have here n times log of g, and log of g is minus 8. And this is the exponential eta transpose the summation of u's. So the calculation that we did rapidly at the end of the lecture on Monday was to take derivatives of this with respect to eta so we can find the maximum likelihood estimate of the canonical parameter theta. And so if the derivative of A will give us basically the expectation of u times n, and this will be, if we differentiate with respect to eta, we get the summation of u's. So immediately you see that by doing this calculation at the MLE point, the expectation of u comes to be the sample mean of the u's. Okay? And the idea here is you don't really need to compute eta at the maximum likelihood point to do this calculation. All right? So effectively, there's no eta here explicitly, even though we derive this at the MLE point. Okay? So one of the calculations we did, I think there's an example on the following slide, was to do this and then using the expectation of u, all right? I think let me just show it rapidly. So we did this for the word distribution, for the Bernoulli distribution. So we computed the expectation of x to be the sample mean of the u's, which is basically the indicator function because x can be 0 or 1. And once we compute the mean mu, effectively from the relation of eta and mu, we can calculate the MLE estimate as log of mu divided by 1 minus mu. Right? So we don't need to compute first the parameters and then do calculations. This comes, as a second step because this is a straightforward first step, and then using that mu, we can compute the eta at the MLE point. Okay. Now, things we did a little bit complicated, but remember in statistics, all equations, even if they look complicated, they come from trivial first steps, okay? There's nothing really complicated. They may look complicated, but they come from trivial equations. So let's see what is that. So let me see if I need to go on this first. Yes, so let me start with this one. So let's assume that our likelihood comes from an exponential family of distributions. Okay? Nothing particular. So again, the same equation. And so this is from where our likelihood comes. And we're asking the following question. What is the prior, or what is the form of the prior that is conjugate to this likelihood? And you remember what does conjugate means? So when do we say that the prior will be conjugate to the likelihood? When? Say it with words. When is a prior conjugate to the likelihood? So when the posterior has exactly the same form as the prior. So effectively, the only thing that I need to do going from the prior to the posterior is update the parameters of the posterior to account for the data that we received. That's when we call it a conjugate prior, and obviously it's a fantastic thing if you can have a conjugate prior because, if you know the posterior, it better look exactly like that prior, okay? So For the exponential family, and I mean, you can just actually look, we can immediately see that there is a conjugate prior that extrapolating from this form of the exponential family on the top, we can see that a prior that has this form of the second equation will actually do the job. Let's see why. Will you agree with me that, so we need the posterior, when we multiply these two, to have sort of this form. So g to some power. Will you agree with me that if I multiply this g without g, that I will get g to some power? Right? Nice. Will you agree with me if I multiply this exponential with the exponential on the first equation, I will also get exponential of theta transpose times something? Done. All right? So our conjugate prior is something that looks like this equation here. Obviously, this is part of the exponential family, right? You can see it as well. And I'm only going to modify it as it is needed, I think, on the next slide. And the reason that I'm going to modify it will come up, when we start doing some calculations with it. So the modification will be the following. This tau zero that I have here, I'm going to write it as the exponent mu zero times tau zero bar, just some scaling. You will see in the next slide why this will make equations look nice, okay? So that it is not needed for any other reasons, but only to make the equations look nice. So apart from that, there is really nothing. So basically, you remember this term here is the log of that, right? So minus the log of that, so I have mu zero times this function a, which is the log of g. Okay. So, and of course, if you want to write this prior in a normalized form, you're going to have this exponential divided by some normalization factor that is nothing else but basically the integral in the parameter space of this exponential on the top. Okay? And by the way, you notice here I'm integrating in theta, all right? And it will come apparent what theta is, but whatever parameters we're using inside the description of theta. So it can be the mean or the variance or things like that, and we will discuss this shortly. Now, I want you to remember this z factor, because I'm going to throw the z factor in some of the calculations I will do, because these normalization factors are very important for model selection and model comparison, which we will revisit next week. So I want you to remember z is just a normalization factor of this prior. Okay. Here's a proof that the posterior will have exactly the same form as the prior. Will you agree with me that if I have n data points, I'll get the equation at the top? I wrote this equation in a previous slide, right? The product of the h's, okay? We don't really care because there are no parameters there. Then g to a power n, and eta transpose the sum of the sufficient statistics. Nothing special, all right? Again, the equation looks that it's going to give you a headache, but I basically multiply the exponential family equation there, okay? Now, will you agree with me that the prior, we just said it before, it is, you remember there was a tau zero here that I wrote as mu zero, tau zero bar, minus a times mu zero, all right? So let's multiply them. If you multiply them, what will you get? N there, and mu zero there. If I let me use the expression on the left of the prior. So I'm going to get n plus mu zero, right? Nice. And then I'm going to get eta transpose, the summation of u's, plus mu zero times tau zero. Looking at the term inside the parenthesis, can somebody guess why I used the notation mu zero tau zero bar instead of just tau zero? I said it will make the equations look nicer. Why did I instead of tau zero that I had, I put it as mu zero tau zero bar? Can you look at this expression and see what the reason may be for that? What is the summation of u, right? If I divide this by n, is the sample mean of u's, right? So this term is n times u bar. You agree? Where u bar is the sample mean. So I wanted to have a similar form, because one of the nice things